Hello and welcome to this video. A special welcome to those who are new to the channel. Make sure you subscribe to the channel if you are new and hit the bell icon so that you can get notified about more upcoming videos on Python programming. Once Python standard library is complete, I will give more problems. We will practice problems and then we will move on to web development. Once I cover JavaScript and Node.js, front-end and server-side programming and SQL, we will come back to Python to make web applications using Flask, Django, and Fast API. Three frameworks will be covered. So we will resume where we left off in the last video. That is, we were dealing with the operations on integers. So we will resume here. All numbers.real types int and float also include the following operation. Math.truncate x truncated to integral. That is the closest integer, which is truncated means it is will be floor. Rounding we have studied. Floor and ceil, I think we have covered this. So we will move on to integer Boolean operations on integer types. So the Boolean operations are OR, XOR, XOR and left shift, right shift. I think we covered this also. So left shift by n bits equivalent to multiplication by power 2 to the power n. Right shift by n bits is equivalent to floor division by power 2 to the power n. Performing these calculations with at least one extra sign extension bit in a finite 2's complement representation, a working bit width of 1 plus max x into bit length comma y into bit length or more is sufficient to get the same result as if there were infinite number of sign bits. Now we move on to additional methods on integer type. So the int type implements number.integral abstract base class. In addition, it provides a few more methods. Int.bitlength is a method which will give the number of bits necessary to represent an integer in binary, excluding the sign and leading zeros. So suppose number is minus 37, its binary would be minus 100101. So as you can see, the number of bits required are 6. Then the description is given more precisely. If x is non-zero, then x.bit length is the unique positive integer case such that 2 to the power k minus 1 less than equal to absolute less than 2 to the power k. Equivalently, when absolute of x is small enough to have a correctly rounded logarithm, then k is equal to 1 plus int log of absolute of x comma 2. This is base 2, the absolute value base 2. If x is 0, then x dot bit length returns 0. Now if you see 37, then the absolute value of x would be 37, and when you take log of that with base 2, it will be 6, because 2 to the power 5 is 32. So this will return 32. In fraction, when converted to integer, it will become 5 point something. So int will give 5 plus 1 6. So that is the formula. So this is equivalent to, this function is equivalent to, you convert it to bin and you left strip minus 0b and then return length of this string. The next function is bit count. So bit count will represent number of ones in the binary representation of the absolute value of the integer. This is also known as the population count. So if the number is 9, you see there are 3 ones. So bit count would be 3. And for minus n also, bit count would be 1. And you can implement this function like this: bit count self return bin self dot count 1. Next function is int dot 2 bytes, where it takes 3 arguments. Length is equal to 1, byte order is equal to big, signed is equal to false. So 1024 to bytes. Okay, so length is 2, byte order is big. So it now big means big Indian and little Indian. In big Indian, the most significant bytes appear at lowest addresses. That is, when they will be printed, they will be directly convertible to the number. So for example, this is 400. Now 400 you multiply first with 16 and second with 256. 256 into 4 is 1024. Now if you convert it to 10 bytes and byte order is big, then it will be populated with leading zeros for 8 bytes and last 2 bytes will contain 400. Similarly, when minus sign is populated, infinite ones will be populated on left hand side, which will become FF, and then 1024 will be represented by FC00. This is 2's complement of minus 1024. If it is 1000 and the number of bytes says x dot bit length plus 7, that is 8, and byte order is little, then it will be XC803. So this you can convert from hex to decimal and you will find this is 1000. Now in Little Endian, 03 should be put first. So the number is actually 3E8 because Little Endian, the most significant bits are at the higher addresses. The integer is represented using length bytes and defaults to 1. An overflow error is raised if the integer is not representable within the given number of bytes. The byte order argument determines the byte order used to represent the integer and defaults to big. If byte order is big, the most significant byte is at the beginning of the byte array. If byte order is little, the most significant byte is at the end of the byte array. The signed argument determines whether 2's complement is used to represent the integer. If signed is false and a negative integral is given, an overflow error is raised. The default value for signed is false. The default value can be used to conveniently turn an integer into a single byte object. So if you convert 65 for example, then the ASCII value is A. However, when using the default arguments, don't try to convert a value greater than 255 or you will get an overflow error because the length is by default 1. So 1 byte can represent only up to 255. So if you want to convert more than 255, you have to give length. And this is the equivalent implementation. So n is the value which you want to convert, length is 1, byte order is big and sign is false. So if byte order is little, you convert it using range, that is your order. And then if it is big, then you invoke reversed on that. And once you have found the order, you extract this from I, you iterate over it, and you implement this formula to get the desired result. Next is int.from bytes. Return the integer represented by the given array of bytes. It takes bytes, byte order and signed, and plus it tables. So from bytes you convert it into integer. So it is a reverse operation. The argument bytes must be a byte-slice object or an iterable producing bytes. The byte order argument determines the byte order. It's the same thing which we have seen. The signed argument indicates whether 2's complement is used to represent the integer. And this is the equivalent function for this from bytes function. Int as integer ratio. Return a pair of integers whose ratio is equal to the original integer and has a positive denominator. The integer ratio of integers whole numbers is always the integer as the numerator and and 1 as the denominator. Int is integer, it will return true for integer types. Now we look at additional methods on float. The float implements numbers.real abstract base class. Float also has the following additional methods. Float as integer ratio. Return a pair of integers whose ratio is exactly equal to the original float. The ratio is in lowest terms and has a positive denominator. That means it gives us a reduced fraction if you invoke it on a float. Raises overflow error on infinities and a value error on nans. Since floats can be infinity and nans, you can't represent them as integer ratio. So an overflow and value error will be raised for them respectively. Float is integer. Returns true if the float instance is finite and with integral value and false otherwise. So -2 is an integer, 3.2 is integer, false. So when the fractional value will be 0, it will return true. Two methods support conversion to and from hexadecimal strings. Since Python's floats are stored internally as binary numbers, converting a float to or from a decimal string usually involves a small rounding error. That is because how the binary conversion, you get infinite number of bits. So there is a mathematical theorem related to this, that suppose there is a fraction p by q which is in decimal. So if q has factors other than 2 that cannot be represented accurately in binary because it will never terminate. So the factors can be of the denominator, factors can be like 3. So for example, 1 by 6, the factors are 2 and 3. It won't be exactly representable in binary numbers. So theorem goes like this. Suppose your base is B and target is T, base T, and T has prime factors T1, T2, T3 and so on up to Tn, and base has factors B1, B2, B3 up to Bm. Then B1, B2 up to Bm should be a subset of target. That is, denominator when factorized should contain values only from T1 to Tn. If that is the case, then fraction will be exactly representable in the target base. Otherwise, it will not be. Float.hex returns a representation of a floating point number as hexadecimal string for the finite floating point numbers. This representation will always include a leading 0x and a trailing p and exponent. Now you can create a float from hex. So if you have a hexadecimal string, you can convert that string into a float. Note that float.hex is an instance method while float.fromhex is a class method. That means float.hex you have to invoke on a float, while float.complex can be invoked on a string. It is not invoked on a float. So this is the representation or format of floating point numbers, where the optional sign may be either plus or minus. Integer and fraction are strings of hexadecimal digits, and exponent is a decimal integer with an optional leading sign. Case is not significant, and there must be at least one hexadecimal digit in either the integer or the fraction. This syntax is similar to the syntax specified in section this of 6.4.4.2 of C99 standard, and also to the syntax used in Java 1.5 onwards. In particular, the output of float.hex is usable as a hexadecimal floating point literal in C or Java code. And hexadecimal strings produced by C's %f format character or Java's double.2 hex string are accepted by float from hex. Note that the exponent is written in decimal rather than hexadecimal, and that it gives the power of 2 by which to multiply the coefficient. So for example, if this is the float, then this 10 is not hexadecimal. Okay, this is basically a decimal value. So 3.A7 will convert to 374, and then that would be multiplied with 10. So if you convert it into float, from float to hex, then it will be 0x1.d38000p plus 11. Applying the reverse conversion to 3740 gives a different hexadecimal representing the same number because of loss of characters. Hashing of numeric types. For numbers x and y possibly of different types, it's a requirement that hash x is equal to hash y whenever x is equal to y. We will see the hash functions later on when we encounter it. This is in the reference, this is not in the library, so let's go and see there. So hash called by built-in function hash, and for operations on members of hashed collections including set, frozen set and dict. The hash method should return an integer. The only required property of that object which compare equal have the same hash value. It is revised to mix together the hash values of the components of the object that also play a part in comparison of objects by packing them into a tuple and hashing the tuple. For example, if you want to hash some object, then you should use all the parts and put them in a tuple and then hash the tuple. Hash truncates the values returned by object's custom hash method to the size of pwise s size underscore t. This is typically 8 bytes on a 64-bit builds and 4 bytes on 32-bit builds. If an object's hash must incorporate on builds of different bit sizes, be sure to check the widths on all supported builds. An easy way to do this is Python-c import sys print sys.hashinfo.width. if a class does not define an equality method, it should not define a hash operation either. If it defines equality but not hash, its instantiation will not be usable as items in hashable collections. If a class defines mutable objects and implements an equality method, it should not implement hash. Since the implementation of hashable collection requires that a key's hash value is immutable. If the hash object's hash value changes, it will be in the wrong hash bucket. User-defined classes have equality and hash methods by default. With them, all objects compare unequal except with themselves. And x.hash returns an appropriate value such that x is equal to y implies both x is y and hash x is equal to hash y. A class that overrides equality and does not define hash will have its hash implicitly set to none. So the key point here is that user-defined classes have equality and hash methods by default. This is a very key point given here. Also, if there is something mutable in the class mutable objects and that implements equal method, then you should not implement hash. So these are the key points which we can take from here. A class that overrides equality and does not define hash will have hash implicitly set to none. When the hash method of a class is an instance of that class will raise an appropriate type error when a program attempts to retrieve their hash value, and will also be incorrectly identified as unhashable when checking is instance obj collections.abc.hashable. If a class that overrides equality needs to retain the implementation of hash from a parent class, the interpreter must be told explicitly by setting hash is equal to parent class.hash. If a class does not override equality wishes to suppress hash support, it should include hash is equal to none in the class definition. A class which defines its own hash that explicitly raises a type error would be incorrectly identified as hashable by is instance object collection.abc.hashable call. The key point which we have is that if we are overriding equality method and we retain the implementation of hash which is defined in a parent class, then we should set the hash to parent class.hash. By default, the hash value of str and object bytes are salted with an unpredictable random value. Although they remain constant within an individual Python process, they are not predictable between repeated invocations of Python. So this is a key point that, for example, if you compare hash of a string and put it in database, the next time when you will compute hash and put it in the database and the Python process has terminated and restarted, then the new hash value will be different. So you should be careful with that. And that's why hash should be computed with the functions which are supplied like SHA-512, SHA-256. Those kind of hash functions should be used to compute the hash, and hashing should not be computed manually because writing a good hash function is very tricky. This is intended to provide protection against a denial of service caused by carefully chosen inputs that exploit the worst case performance of a dict insertion O(n) square complexity. Changing hash values affects the iteration order of sets. Python has never made guarantees about this ordering, and it typically varies between 32-bit and 64-bit builds. So this is something we will study for more, but for now I'll stop here because I don't want the video to be very long. So I'll see you in the next video and we will continue the hashing of numeric types there. So I hope that you have found this video useful and informative. If so, please like the video, share on social media as much as you can, and make use of comment box to speak your mind. I would like to interact with you guys, whether you are a veteran programmer or intermediate or a newbie. You might have some ideas which I would like to learn, and I would like to understand how you think about programming, and we can discuss about programming. So make sure to use the comment box to speak your mind, and I'll see you in the next video. Thanks a lot for watching. Happy programming.